right, so now we're ready for part 2, the linear speed of a rotating system. And so here's what you should know now. You should know what linear distance is, linear speed, and linear acceleration when you're going sideways. And then you should also know what rotational distance, rotational speed, and rotational acceleration are. But the goal for part 2 is to be able to predict the linear speed if you know what the angular speed is, or if you know what the linear speed is, to be able to predict what the angular speed is. So that's going to be our goal for this particular part of the lab. Now we need to go back to the lab here, and you need to click on reset. So reset everything, okay, and then type back in what your original numbers were. So the original angular velocity in degrees, so click on here for degrees, type in 30. So that was the original angular speed of the turntable. And then the acceleration should be 0. The angle should be 0. There's the ladybug right there. Okay, so now let's go back to the lab here. And it says to reset the angular acceleration back to 0, show the graphs, click on theta, omega, and v. Theta, omega, and v. So that is going to be this one down here, theta, omega, and then v. So this is going to tell you the angular distance, the angle that it rotates through. It's going to be telling you what the angular speed is, radians per second, and then it's going to be telling you what the linear speed is. So let me go ahead and click on the angle in radians here. Okay, so it changed this number. So this is angular speed in radians per second, and then this is going to be the linear speed in meters per second. Now notice where the ladybug is at. Also, I want you to notice what is the initial linear speed. It's 0. Why do you think it has no linear speed? Well, because it has no angular speed. So if this one up here it starts out at 0, then this one is also going to start out at 0. So it's not moving, so it has no linear speed. Okay, so now let's go down to the lab, see what to do next. So we've noted the linear velocity, or the linear speed. You may need to click the plus symbol on the graph to expand it so that you can read the velocity, but trust me, it's going to be 0. Click on the ruler at the bottom of the simulation and measure the radius from the center of the turntable to the ladybug. So if we go back to here, we need to find the ruler. So the ruler is down here. So click on that. Okay, there's your ruler. That is not in inches. It's in meters. That is one big turntable. So you'll notice the numbers on this are going to be in terms of meters. So those are not in terms of inches. So you can go to your table here, and we're going to say measured angular velocity from the simulation. So measured angular velocity. So it's going to be that number there. Measured radius with your ruler. So put that there. Okay, now we need to turn on the simulation and measure the linear velocity of the ladybug. So again, we could let it go through what 90 degrees if we wanted to. So now we're going to hit the go button. And then we could stop it up there somewhere. And now look at the velocity. So here's the angular velocity right there. And then it doesn't have a box for it, but you can measure it. So you might need to click on these buttons to expand the graph so that you can read the number, but it's up here. So here's the speed in meters per second. So you're going to take that number and then put that right here. And now we want to calculate it. But we don't know how to do that yet. So leave that one blank. And so let's go down here. It says now to move the ladybug further from the center of the turntable. So what you can do is go back to the simulation. You're going to grab the ladybug and you can move her. Now when I moved it, you see that it made the turntable start going again. Now if you, and just ignore this part right here and ignore this part here. So we want to move the ladybug so that she is, let's say, at the edge of the table. And now you should notice, see this? It changed. So you had this velocity right here, and now you've got this velocity when you move the ladybug to the outside. So you could just read this number right here. So that's important. So if we move the ladybug to the outside, then that did something to the speed. So I'm trying not to give away the answers here. It said to move the ladybug further from the center of the turntable. What happened to the angular velocity? So did the angular velocity get greater? Did it get lesser? Or did it stay the same? So look at your data from the simulation. Now look at the linear velocity. Did the linear velocity get greater? Did it get smaller? Or did it stay the same? So if you move the ladybug further away from the center of the turntable, what happened to the angular velocity and what happened to the linear velocity? That's what you should be paying attention to. Because the angular velocity and the linear velocity are connected by this formula here. So that the linear speed of something that is rotating is equal to the angular speed at which it's rotating multiplied by the radius. So I want you to calculate the linear velocity. So you, at this measured radius, you should now have the omega. You should know what the radius is, and you should be able to calculate its linear velocity. So you'll put that, measure it, and then calculate it, and put it in these two boxes. And they should line up pretty much the same. And then you, if you want, I don't have another set of columns over here, but if you wanted to, you could do it again by moving the ladybug somewhere else, measuring its radius. So this number is still going to be the same. The omega doesn't change, but the R is, and that's going to change the V. So you might want to just make sure that that's true. But the point is now that you can use this formula to calculate the linear velocity if you know the angular velocity. Or if you were given this, you could calculate that. All right, let's take a break. When we come back, we're going to do part 3 of the lab, which is on rotational inertia, torque, and Newton's second law.